Welcome all to the Module 12 WLAN concepts. Wireless networking is one of the most popular and fastest growing technologies on the market. How many of you use a wireless connection at home, work, or school? Almost everyone. Ever wonder how it works? There are many ways to connect wirelessly. Like everything else involving networks, these connection types are best suited for particular situations. They require specific devices and are also prone to certain types of attacks. And of course, there are solutions to mitigate these attacks. Sounds interesting, isn't it? The WLAN concepts module gives you the foundational knowledge you need to understand what wireless LANs are, what they can do, and how to protect. So if you're curious enough, why wait longer? Let's get started. So these are the different topics that we're going to cover as part of this module. Let us talk about introduction to wireless networks. What are the components of WLANs? How does a WLAN operate? What do you mean by CAPWAP operation? How do you manage the channels of wireless networks? What are the different threats that usually WLAN faces? And finally, how do you secure WLANs? What are the different security mechanisms that we can implement? So first, let's talk about the introduction to wireless. Now, generally, you must have come across a Wi-Fi router somewhere, wherever you go. Most of them have one in their homes now, because it's very convenient to connect as many number of devices that you want while giving you the mobility. So a wireless LAN or WLAN is a type of wireless network that is commonly used in homes, offices, and campus environments. Almost all the academic institutions nowadays have Wi-Fi on their campus. They say that it's a Wi-Fi enabled campus. So the students, irrespective whether they're carrying mobile phones or laptops or some other electronic devices, they can connect to a network irrespective of where they are, whether they are in a classroom or something like that. As long as they're in the campus, they must have some type of Wi-Fi coverage. All the academic institutions are providing this. WLANs actually make mobility possible within the home and business environments. The infrastructures which actually support such wireless networks rapidly change, so that they keep on adapting, they keep on evolving to actually provide the comfortable nature to these kind of devices. So that whatever new technologies they come, or whatever new types of devices that they come, the wireless networks are keep evolving, they are keep on evolving from day to day. Now, so let us talk about the different types of wireless networks that you see regularly. The first one that you come across is a wireless personal area network, which is a low power and a short range, usually 20 to 30 feet or 6 to 9 meters. This is based on the IEEE 802.15 standard and works the 2.4 gigahertz frequency. The best known examples for this type of wireless network is Bluetooth and Zigbee. The second category comes from WLAN or wireless LAN. These are medium-sized networks of up to about 300 feet. This is solely based on the IEEE 802.11 standard and 2.4, and this works in either 2.4 or 5 gigahertz frequency. The third one is the wireless MAN, which covers a large geographical area such as a city or a district, and they use specific licensed frequencies. And again, we come across the wireless WAN networks, WWAN. These are extensive geographic area for national or global communication. Once again, they use specific licensed frequencies, not the 2.4 or the 5 gigahertz bands. So of which the first, let us talk about Bluetooth. So the IEEE WPAN standard used for device pairing at up to 300 feet or 100 meters distance. There are two types of Bluetooth radios. The first one is the BLE, which stands for Bluetooth Low Energy, which supports multiple network technologies, including mesh topology to large scale network devices. The second variant of the Bluetooth radio is called as Bluetooth Basic Rate or Enhanced Rate, BR/EDR, and it supports to point-to-point topologies and is optimized for audio streaming. The second option that we have is something called as WiMAX. It stands for Worldwide Interoperability for Microwave Access. It is based on the IEEE 802.16 WWN standard that provides high-speed wireless broadband access of up to 30 miles or even 50 kilometers. This operates similar to Wi-Fi, but it provides even great speeds over great distances and for a large number of users. Imagine maybe one or two towers that covers an entire city. That is the concept behind WiMAX, which stands for Worldwide Interoperability for Microwave Access. So moving on, the next category that we find is cellular broadband. most of the people now have a mobile phone in their pocket, and a mobile phone without an internet is almost useless. So everybody has a data connection, irrespective. Some people have 4G, some people have 3G, some people even have 5G. You must understand that the cellular broadband has got the capability. It is a multi-access network where it has the capability of carrying both the data and voice communications. Usually it works on the concept of cell sites. A cell site is created by a cellular tower transmitting signals in a given area. The area through which this coverage is called as a cell. The two types of cellular networks are, the first one is the GSM one, which we use extensively, Global System for Mobile Communications. It is internationally recognized. And the second variant of cellular broadband is your CDMA, Code Division Multiple Access, which is primarily used on the USA. So the other variant where we can actually have a wireless network is satellite broadband, which provides network access to remote sites through the use of a directional satellite dish that is aligned with a specific geostationary Earth orbit satellite. It is more expensive and it is only used because it needs to have a clear line of sight. It is normally used when you don't have a cable or a DSL in that particular area. They're used by rural homeowners or even businesses. Because it is an expensive option, we find this less used one. So the other one which we have is, we are going to talk about the 802.11 standards of your Wi-Fi, of the Wi-Fi. So these standards actually define how radio frequencies are used for wireless links. Nowadays, most of the devices that we are using do support 802.11 AC and 802.11 AX. Earlier days, we used to have 802.11 A, 802.11 B, G, and N. You can see here, usually the evolution, the data rates keep increasing. Now, with 802.11, the original standard, which worked at 2.4 gigahertz, the data rates are only 2 Mbps. Then came B, which actually bumped up the data rates up to 11 Mbps. And then came A, which works in the 5 gigahertz band. So it's a small coverage area, less effective at penetrating building structures. And it is not interoperable with either 802.11b or 802.11g. Then came the 802.11g standard, which worked with the 2.4 gigahertz band, where the data rates have gone up to 54 Mbps, and it is still backward compatible with 802.11b standard. Then came the 802.11n, which works in both bands, 2.4 and 5 gigahertz band, where the data rates supported are 150 to 600 Mbps, and the distance range is up to 70 meters, 230 feet. It requires multiple antennas with MIMO technology. Then the two new ones is 802.11 AC, which works in the 5 gigahertz band, where the data rates supported are between 450 Mbps to 1.3 Gbps. It supports up to 8 antennas, backward compatible with 802.11 AN devices with the limiting data rates. 802.11 AX, also called the Wi-Fi 6 or High Efficiency Wireless, HEW. It provides improved power efficiency, higher data rates, increased capacity, and handles many connected devices. And it is the only standard which is capable enough of using the 1 gigahertz and 7 gigahertz frequencies also. It works currently both in the 2.4 and 5 gigahertz bands as well. So any radio frequencies you talk about, they all belong to an electromagnetic spectrum. The spectrum you can see here, we have from the low frequency waves to the high frequency waves, and each and every range of frequencies have its own specified set of applications. You can see there are some given X-rays, gamma rays, ultraviolet rays. The 2.4 gigahertz is called as ultra high frequencies, 802.11 B, G, N, and AX. The 5 gigahertz or super high frequencies is 802.11 A, N, AC, and AX. My suggestion for you to understand the spectrum of radio frequencies is just Google it, type in electromagnetic spectrum, and you can see different images, with each image giving you the different range of frequencies and the types of communication or the different types of applications that use in that particular frequency area. Just go there. Here we are actually specifying it for only 2.4 gigahertz and 5 gigahertz. Now, somebody has to control these things, right? Because we have numerous number of vendors that manufacture devices to work with your Wi-Fi standards. So who controls them? We need a standard. So why we need standards? Because standards ensure interoperability between devices that are made by different manufacturers. Internationally, there are 3 organizations that influence your WLAN standards. The first organization that we talked about is your International Telecommunication Union, ITU. This regulates the allocation of radio spectrum and satellite orbits. Generally speaking, ITU has got two branches, ITU-T and ITU-R. ITU-T stands for ITU telecommunications sector, and ITU-R stands for ITU radio communications sector. After ITU, the next thing we talk about is your IEEE, Institute of Electrical and Electronics Engineers. This specifies how a radio frequency is modulated to carry information, maintains the standards for local and metropolitan area networks, MAN, LANs and MANs, with the IEEE 802 LAN MAN family of standards. All the things that you see, 802.11, 15, 16, all those come from IEEE itself. The last one is something called as Wi-Fi Alliance, which promotes the growth and acceptance of WLANs. It is an association of vendors whose objective is to improve the interoperability of products that are based on the 802.11 standard. We call it as Wi-Fi Alliance. So this is all the introduction part to wireless. You need to understand that wireless is nothing but a lot of frequencies, and different applications use different frequencies because of the characteristics that are present. So let's talk about what are the important components that make up a wireless local area network. The first thing that you need to understand is any deployment, any wireless deployment requires at least a minimum of two devices. One should be a transmitter and there should be a receiver which is tuned to the same frequencies. Now, there might be an end devices with the wireless network interface cards, a network device such as a wireless router or a wireless access point. To communicate wirelessly, generally, all these latest electronic gadgets do integrate wireless NICs that incorporate a radio transmitter or receiver. In some cases, when you're using old age laptops, when you don't have an inbuilt Wi-Fi antenna, then you can even go for a wireless USB wireless adapter. In some cases where you have some of the home PCs, not laptops, home PCs, they might not have the WLAN adapter into it. You can just buy an USB adapter, plug into it and connect it to the Wi-Fi itself. You need not have an Ethernet connection also. The next thing is, let us talk about the most important one and the most common device that you see every day, which is nothing but your home router. The type of infrastructure device that an end device associates and authenticates with there is based on the size and requirement of the WLAN. So the wireless routers, what role do they play? This is simply one. It actually has it acts as an access point. It does act as a switch. It does act as a router. So it provides wireless access to by acting as a wireless point. And if you can see, if you turn back your wireless router, you can see some of the ports which support the Ethernet connectivity. Usually a home router provides a 4-port full duplex 10,100,000 Ethernet switch to interconnect wired devices. The third one is the router, because it provides a default gateway capabilities for connecting to other network infrastructures such as internet. You know how a wireless connection is made. So your devices wirelessly discover the SSID and attempt to associate and authenticate with it to access the local network and internet. Most wireless routers also provide advanced features such as high-speed access, support for video streaming, IPv6 addressing, quality of service, configuration utilities, and USB ports to connect to printers or even portable drives. You can see most of the routers. We are all using these type of facilities and features. Now, home users who want to extend their network services can implement something called as Wi-Fi range extenders. They are also available on the market. A device can connect wirelessly to the extender, which boosts its communications to be repeated to the wireless router. So if you want to extend your Wi-Fi coverage in your home, you can, rather than purchasing a new router and extending and then purchasing an Ethernet cable to connect from one router to another router, you can simply get a Wi-Fi extender. Now, what do you mean by wireless access point? The wireless clients use their NIC to discover the nearest access points. So clients then attempt to associate and authenticate with an access point. After being authenticated, the wireless users can have access to the network resources. Access points are nothing but your the routers. Whenever your device boots on, it first searches for an access point. Only after it finds an access point, it announces itself. It then authenticates, and then an association takes place. We'll discuss about that. Okay. So what are the different categories of access points? So APs can be categorized as either autonomous APs or controller based APs. Please understand the subtle differences here. Autonomous APs are standalone devices which are configured through a CLI or GUI. Each autonomous access point acts independently of the others and is configured and managed manually by the administrator. Whereas The second variant, called as control-based access points, they are known as lightweight APs or LAPs. They use something called as lightweight access point protocol, LWAPP, to communicate with a WLAN controller or WLC. From here onwards, we will be calling them as WLC, WLAN controller. And each LAP is automatically configured and managed by the WLC. Here, the administrator need not go and manually configure each and every access point. These are called as controller-based APs. The other ones are called as autonomous APs. These are standalone devices. You need to configure them manually only. So let us talk about antennas also, because antennas play a crucial role. Usually there are three types of external antennas. The first one is omnidirectional. It provides a 360-degree coverage. If you want to implement a wireless network in your home or in your office, you can just go there, get this omnidirectional antenna, which you see in most of the routers. The second one are directional. These focus the radio signal in a specific direction only. The Aggie on the parabolic dish are the best examples of a directional antenna. The third one is something called as MIMO, multiple input, multiple output. These actually uses multiple antennas up to 8 to increase the bandwidth. Okay, most of the latest standards do implement MIMO standard. So how does a WLAN operate? Let's talk about the operation of a WLAN. So first thing you need to understand that there are different topology modes. These the 802.11 standard identifies two main wireless topology modes. The first one is ad hoc mode and the second one is a infrastructure mode. There is a third mode called as tethering, which sometimes you might have used your mobile phone as a hotspot to connect to your laptop, maybe to download or check your email, something like that. It provides a quick wireless access. It doesn't give you the best bandwidth, but still it can also be used. The first mode is ad hoc mode. The name itself suggests on demand. So it is used to connect clients in a peer-to-peer manner without an access point. There is no access point here. The client itself creates this network, and the 802.11 standard refers to an ad hoc network as an IBSS. We also call it as independent basic service set. An IBSS is nothing but a 802.11 network working in an ad hoc mode where there is no access point. The clients itself, they join with one another to create such a network. Whereas the other way of it is an infrastructure mode, where the clients connect to the network using an access point. This is all planned in advance. We have a distribution system connecting one access point to another access point, all those things. The APs connect to the network infrastructure using the wired distribution system such as your Ethernet. The third mode, as I just told you, is called as tethering. It is a variation of the ad hoc topology where a smartphone or a tablet with cellular data access is enabled to create a personal hotspot. Most of us must have used this thing. That is called as tethering mode. Okay. So what do you mean by this BSS? Now, infrastructure mode defines two topology blocks. The first one is something called as BSS, which stands for Basic Service Set. It consists of a single access point interconnecting all associated wireless clients. You can see in this diagram here, there are two BSS. The circles depict the coverage area for the BSS. So you can see the circles over here, which actually tell you what is the coverage area. This coverage area is also called as BSA, Basic Service Area. If a wireless client moves out of its BSA, it can no longer directly communicate with other wireless clients within that particular BSA. The layer 2 MAC address of the access point is used to uniquely identify each BSS, which is called the BSSID, Basic Service Set Identifier. Therefore, the BSSID is the formal name of the BSS and is always associated with only one access point. So the MAC address of the access point is used to uniquely identify the particular basic service set. The other one is something called as ESS. ESS is nothing but when you join these BSS together. So we say when a single BSS provides insufficient coverage, what you do is you actually combine two or more BSS through a common distribution system. You can see here, there is one BSSID, there is another BSSID, and all of them are combined with one another to create a ESA. That is nothing but extended service area. So roaming mobile wireless clients can move from one BSA to another within the same ESA, and they can still seamlessly connect. This is the kind of model that we use in large campuses. You have this particular ESA where you connect your mobile phone to one access point, and if you keep moving through your college also, that means you will keep on changing your access points, but still you will not lose network connectivity. So that rectangular area in the figure depicts the coverage area within which the members of an ESS may communicate. This area is called as the Extended Service Area ESA, which is similar to the BSA, which is nothing the coverage area of one BSS ID. So you need to remember these things. BSS stands for Basic Service Set, and when you combine multiple BSS, we call it as ESS, Extended Service Set. So we covered the 802.3 frame structure in our earlier videos in our ITN modules. So the 802.11 frame format is very much similar, but it contains more fields. You can see here we have a frame control, duration ID, address, sequence control, address domains. In frame control, once again, we have the protocol version, type, subtype, to distribution system, or it is coming from DS. All these ones means they are flags. They are either true or false. That's all. Retrieve flag is there, power management is there, more data is there, WEP is there or not, the order flag is set or not. So all these things are in your 802.11 frame structure. Unlike 802.3 standard, 802.11 standard has got many fields in it. So if you remember correctly, in Ethernet, I discussed about CSMA-CD operation, which stands for collision detection. But WLANs are half duplex and a client cannot hear while it is sending, so making it virtually impossible for a client to detect a collision. Hence, we use a new version of the protocol, CSMA protocol, called as CSMA-CA protocol, where CA stands for collision avoidance. So CSMA-CA stands for carrier sense multiple access with collision avoidance to determine how and when to send data. The steps are simple. So first, a wireless client, when it wants to send data, it listens to the channel first. That is what carrier sense stands for. If there is no other traffic currently on the channel, it does not immediately send the data, but it will send something called as an RTS message. RTS stands for ready to send. And this message, the AP is to request dedicated access to the network. Once, if there is no other station competing, it will actually receive something called as CTS, clear to send message from the access point, granting the access to send. Then it waits a random amount of time before restarting the process if it did not receive a CTS message. If it did not receive a CTS message, it assumes that somebody else is using the channel, or it might be there might be some issue with it. If it receives the CTS, it can start transmitting the data. It has to acknowledge all transmissions. If a wireless client does not receive an acknowledgement, it has to assume that a collision has occurred and it has to restart the process from start. So this is how CSMA-CA works, and WLANs do incorporate CSMA-CA because CSMA-CD does not work in wireless networks. Now, how do they associate? How do a client associate with an access point? So for wireless devices to communicate over a network, they must first associate with an AP or a wireless router. There is a three-stage process in that. The first one is it has to discover a wireless access point and then authenticate with the access point. And once the authentication is successful, it can then associate with the access point. These are the three steps: discovery, authentication, and upon successful authentication, you create an association. So to achieve successful association, a wireless client and an IAP must agree on specific parameters. The first parameter is your SSID. The client needs to know the name of the network to connect. Then comes the password. This is required for the client to authenticate to the access point. The third one is the network mode. What is the current standard that it is being used, which is the 802.11 standard. Then comes the security mode. So which security parameter settings are currently being used? Are we using WEP? Are we using WPA or WPA2? And finally, what are the channel settings, the different frequency bands that are in use? All these parameters are being discussed between a client and an access point before the association starts. Okay, so how does it discover? There are two modes once again. One of it is called as passive mode and the other one is called as an active mode. So wireless clients actually connect to the access point either using both, either or both. So generally, let us talk about the passive mode first. Here, the access point openly advertises its services by periodically sending broadcast beacon frames containing the SSID, supporter standards, and security settings. This keeps on saying that I am the access point here. Keeps on sending these beacons. In the active mode, when the wireless client first boots up, if it did not receive a beacon from the access point, then it will send a probe request. So here, for that, it needs to know the name of the SSID. So the wireless client initiates the process by broadcasting a probe request frame on multiple channels. So once it goes here, Then the access point receives it, and then it will send a probe response back. It will tell what is the SSID, what are the supported standards, what are the security settings that it is going to accept, all these things. In either, by using either of these modes, a wireless client can associate itself with the access point. First it discovers, then communicates, authenticates, and then has the association. So what is this CAPWAP operation? Why is it required? Right? So CAPWAP actually stands for Control and Provisioning of Wireless Access Points. It is an IEEE standard protocol that enables a wireless LAN, WLAN controller to manage multiple access points and WLANs. It is based on LWAPP protocol, but it adds additional security with the datagram transport layer security. We will call it as DLTS. Okay, so it encapsulates and forwards the WLAN client and traffic between an access point and a WLC or tunnels using the UDP protocols 5246 and 5247. Here it creates tunnels. It operates both IPv4 and IPv6. Whereas an IPv4 uses IP protocol 17 and IPv6 uses the IP protocol 136 number. So this is CAPWAP actually stands for Control and Provisioning of Wireless Access Points. This is used by a WLC so that it can actually manage the multiple access points and also the WLANs. So if you see here, the CAPWAP split MAC concept does all the functions normally performed by individual access points and distributes them between two functional components. There are two components here. The first one is an AP MAC functions. The second one is WLC MAC functions. You can see in the table here, the access point MAC functions includes beacons and probe responses, whereas the WLC MAC functions include the authentication. Next things, the packet acknowledgements and retransmissions, frame queuing and packet prioritization. The MAC layer data encryption, decryption are all kept under the AP MAC functions, whereas termination of the 802.11 traffic, frame translation to other protocols, association and reassociation of roaming clients are all actually taken over by the WLC MAC functions. This is called as a split MAC architecture. Now, you see, I just told you about the datagram transport layer security, DTLS encryption. So DTLS provides security between the AP and the WLC. So this is enabled by default to secure the CAPWAP control channel and encrypt all management and control traffic between the access point and WLC. You can see the WLC here and you can see the access point here. So whatever traffic is happening here, you can see the CAPWAP control tunnel here and also the CAPWAP data tunnel here. For this CAPWAP control, the DTLS encryption is enabled by default, whereas this is optional and it is only enabled per AP in this particular CAPWAP data channel. It requires a DTLS license to be installed on the WLC before it can be enabled on the access point. So in this, we also come across something called as Flex Connect APs. This Flex Connect actually enables the configuration and control of APs over a WLAN link. There are two modes of operation for the Flex Connect AP. The first one is the connected mode, where the WLC is actually reachable. The Flex Connect access point has the CAPWAP connectivity with the WLC through the CAPWAP tunnel. The WLC performs all the functions. Whereas in the second mode, it is called as a standalone mode, where the WLC is actually not reachable. The Flex Connect access point has lost the CAPWAP connectivity with the WLC. In that case, the Flex Connect access point can assume some of the WLC functions, such as switching client data traffic locally and performing the client authentication locally as well. So these are the two modes in Flex Connect access points: connected mode and standalone mode. So let us talk about the channel management. When you talk about wireless, we have to talk about channels. So generally, if the demand for a specific wireless channel is too high, the channel may become oversaturated, degrading the quality of the communication. Channel saturation can be mitigated using techniques that use channels more efficient. You have multiple techniques. If you study the modulation techniques, or if you are into mobile computing, mobile communications, or wireless communications, or wireless networks, you must have come across these names, definitely, for sure. First one is direct sequence spread spectrum, DSSS, which is a modulation technique which is designed to spread a signal over a large frequency band. It is actually used by 802.11b devices to avoid interference from other devices using the same, which are actually working in the same frequency band. The other option is FHSSS. which stands for frequency hopping spectrum. The name itself suggests you that the signal keeps hopping between different frequencies. This transmits radio signals by rapidly switching a carrier signal among many frequency channels. The sender and receiver must be synchronized to know which channel to jump to. This is the one which is actually used by the original 802.11 standard. The third one, which is currently used by most of the modern day networks, is called as OFDM, orthogonal frequency division multiplexing. It is a subset of frequency division multiplexing in which a single channel uses multiple subchannels on adjacent frequencies. This OFDM is used by a number of communication systems, which includes the current standards of 802.11 A, G, N, and AC, which uses OFDM techniques. And as I told you about the channels, the 2.4 gigahertz band is once again subdivided into multiple channels. Each one is allocated 22 megahertz. You can see in the diagram here, there are many channels, and each one of the channel is 22 megahertz wide, and it is separated from the other by 5 megahertz. The difference between here, you can see the 5 megahertz here. But when you configure the 2.4 gigahertz channel, the best practice is to use the 3 non-overlapping channels, which are the 1, 6, 11. They are actually colored orange in our diagram. You can see here 1, 6, 11. They don't overlap. They don't have coverage area over one another. So in normal tendency, they tend to use these 3 channels while setting up the 2.4 gigahertz. Similarly, when you talk about 5 gigahertz channels, once again, we have 24 channels. Each channel is separated from the next channel by 20 megahertz. Here also, we have 3 overlapping channels, which are 36, 48, and 60. So these 3 channels can be used so that you can actually reuse the frequencies and increase your area of coverage. Whenever you want to plan a WLAN deployment, the things, what are the considerations that you need to make? What are the different things that you need to take into consideration and plan? The first thing is number of users supported by a WLAN. And this obviously depends on some of the following characteristics. The first one is the geographical layout. If you have too many walls or if you have too many rooms, you don't expect the coverage to be the same in all rooms. The number of bodies and devices that fit in a space. And what is the expectancy of the users regarding the bandwidth? Are they expecting 1 Mbps, 2 Mbps, or is anything okay? And also, how do you use the non-overlapping channels? Because we need to set up multiple access points at different parts, at different places to cover the entire area. When you are setting up different access points, what are the channels that you are going to set it up? How, and also what is the transmit power settings for these access points? You can see here in this diagram, the X represent the different access point settings, and the circle actually shows you the coverage area of that access point. You need to make sure that all your targeted area is within the coverage of at least one access point, so that a user roaming in across anywhere in this particular area will still have access to the network. So let's talk about WLAN threats. Now we talked about the introduction to wireless communication, what are the different frequencies, and then we spoke about what are the different components that we have for WLAN, and then we also spoke about the channel management of a WLAN. Now we have come to the part where we need to talk about WLAN threats, because it's an open network. Wireless means open. Anybody who has a receiver does have the capability to receive the signals when they are tuned to the same frequency. So let's talk about WLAN threats. So as I told you earlier, a WLAN is open to anyone within the range of an access point and the appropriate credentials to associate to it. With a wireless NIC and a knowledge of cracking techniques, an attacker may not have to physically enter the workplace to gain access to a WLAN. You must have seen in the movies or different TV shows where an attacker can sit inside a car and still hack your wireless network. Because if your wireless network is good enough, it has a wide coverage area. You need not enter even into your own house to acquire the network. The attacks can be generated by outsiders, disgruntled employees, and even unintentionally by employees. They are susceptible. These wireless networks are actually specifically susceptible to several threats, which include interception of data, where somebody else might be reading your confidential information, intruders, unauthorized users attempting to access the network resources, and denial of service attacks, DOS attacks. The access to the WLAN services can be compromised either accidentally or maliciously. There are many solutions that do exist in order to thwart such attacks. And the last one is something called as rogue APs. These are nothing but the unauthorized access points installed by a well-intentioned user or for malicious purposes can be detected using management software. So it can be if anything. These are all the different types of threats that usually WLANs face. So let us talk about the denial of service attacks. The wireless device attacks can be the result of anything. It can be result of an improperly configured device, some errors, configuration error or something, which can disable the entire WLAN, and maybe a malicious user intentionally interfering with the wireless communication, their goal being to completely disrupt or disable the wireless network so that no device can actually access the medium. The third one is accidental interference, because WLANs are prone to interference from other wireless devices, which includes your microwave ovens, cordless phones, baby monitors, which work in the same frequency bands. There are many ways. These are the common things through which a device attack can happen. To minimize the risk of a device attack due to improperly configured devices and malicious attacks, the first thing we need to do is you need to harden all devices, keep the password secure, create backups, and also ensure that all configuration changes are incorporated off hours where most of the users are not active. Okay, so let's talk about the rogue access points as well. A rogue access point is an access point or wireless router that has been connected to a corporate network without explicit authorization and against corporate policy. Imagine a simple scenario where you are given a room through which you need to work through an Ethernet connection. But what you decide was just to go out and buy a wireless router for about 1,000 rupees or so, and then connect it to your Ethernet cable so that you can have Wi-Fi access within your room, so that you can use your mobile phones or your laptop or some other tab or iPad or something like that. That is also a rogue access point, because that particular access point has been installed without explicit authorization, and maybe you know it or not, it might be against the corporate policy. Once connected, this particular access point can be used by an attacker to capture the MAC addresses, data packets, gain access to the network resources, or even launch a man-in-the-middle attack. So that actually acts as a gateway for an attacker to enter into your network. You might ask me, what about other devices? They might be hardened by they might have proper security mechanisms installed by your network administrator, whereas the router which is installed by you might not. So a personal network hotspot could also be used as a rogue access point. A user with secure network access enables their authorized Windows host to become a Wi-Fi access point. So to prevent such things, organizations must configure the WLCs with rogue AP policies and use monitoring software to actively monitor the radio spectrum for any type of unauthorized access points. It should not be tolerated. It should not be encouraged. The people should not do such things. Okay. So what do you mean by this man-in-the-middle attack? So when you're talking about the man-in-the-middle attack, the name itself is actually self-explanatory. Here, the attacker is positioned in between two legitimate entities or two legitimate communicating parties, such that he is able to read all the communication that is happening between these two parties, or even modify the data as well. A popular wireless MITM attack is called the evil twin access point attack, where an attacker introduces a rogue access point and configures it with the same SSID as a legitimate access point. Defeating such attacks actually begins with identifying the legitimate devices on the WLAN. For this, the users must be authenticated. After all of the legitimate devices are known, the network can be monitored for any kind of abnormal devices or traffic, so that you can pinpoint where these rogue devices are. If you implement such a way, the man-in-the-middle attack at least can be defeated to some point. So how do you secure WLANs? What are we going to do? So to address the threats of keeping the wireless intruders out and protecting the data, two early security features were used and are still available on most routers and access points. The first one is SSID cloaking. Here, what happens is when you want to access a network, whenever you switch your mobile device on, you can see the name of the Wi-Fi networks, right? You can actually configure your access point or some wireless routers to not send the SSID beacon frame. That means the access point will not display the name. It will not send a beacon displaying the SSID name. The wireless client must be manually configured with the SSID to connect to the network. Only the network administrator knows what the name of the network is. In such a case, attackers trying to access the network will not understand or will not know the name of the Wi-Fi network. The second one is your MAC address filtering. An administrator can manually permit or deny clients wireless access based on their physical MAC hardware address. If you are having a device with a different MAC address, you will not be able to join the WLAN. But these two techniques are good enough if you are having a small network, limited number of users, limited number of devices. But modern networks, I don't think these two work because of the huge number of devices or many number of users that come and go or join and leave the network at a regular basis, right? So the next thing we need to talk about is how do you do the authentication? The best way to secure a wireless network is to use authentication and encryption systems. There are two types of authentication which were introduced actually with the very first 8.2.11 standard. The first one is called as Open System Authentication OSA. There is no password required here. Typically used to provide free internet access in public areas like your KFs, airports, and portals. The client is actually responsible for providing security by using maybe a VPN service. The second one is shared key authentication. It actually provides mechanisms such as wired equivalent privacy, WEP, Wi-Fi protected access, WPA, WPA2 and WPA3 to authenticate and encrypt data between a wireless client and access point. However, the password must be pre-shared between the both parties to connect. So let us talk about these things. These are the different shared key authentication methods that we spoke. First one is your WEP, wired equivalent privacy. This is actually specified in the original 802.11 standard, and it is no longer used because it can be broken off very easily. It is no longer recommended and should never be used. The next step is something called as Wi-Fi protected access, which it is a Wi-Fi alliance standard that uses WEP but secures the data with much stronger algorithm called as temporal key integrity protocol encryption algorithm. This changes the key for each packet, making it much more difficult to hack. The next step is your WPA2. This uses the advanced encryption standard, which is currently the strongest encryption algorithm for symmetric keys. The next thing is WPA3. This is the next generation of Wi-Fi security. All WPA3 enabled devices use the latest security methods, disallow outdated legacy protocols, and require the use of PMF, protected management frames. So WPA3 is the current standard which gives you the utmost best security possible. Now, how do you authenticate a home user? The home routers typically have two choices, either go for WPA and WPA2, with WPA2 having two authentication methods. The first one is personal. Here, the wireless clients authenticate with the wireless router using a pre-shared password. There is no special server that is required to authenticate a particular client to the access point. Whereas if you go for an enterprise kind of thing, you can have, or it is required for a remote authentication dial-in user service, also called as radius authentication server. Here, the device must be authenticated by the radius server, and then users must authenticate using the 802.1x standard. This uses the extensible authentication protocol, EAP, for authentication. You can see here WPA and WPA2 include two encryption protocols. The first one is the TKIP, temporal key integrity protocol, and the other one is your advanced encryption standard. So moving on, if you talk about the authentication in an enterprise network kind of setting, this requires an AAA, which stands for authentication, authorization, and accounting radius server. Three pieces of information are required for this to happen. The first one is the server's IP address, and the next one is the UDP port numbers. The UDP ports 1812 for radius authentication, 1813 for radius accounting, but you can also operate using UDP ports 1645 and 1646. And then the most important thing is your shared key, which is used to authenticate the access point with the radius server. So coming to the end, as I told you, WPA3 is the latest version of the security protocol. Because WPA2 is no longer considered secure, WPA3 is recommended whenever available. It includes 4 features. WPA3 is personal. It thwarts the brute force attacks by using simultaneous authentication of equals, SAE. The next feature is WPA3 Enterprise. This uses 802.1x EAP authentication, but it uses 192-bit cryptographic suite, eliminating the mixing of security protocols of your earlier 802.1 standards. The third feature is for open networks. It does not use any authentication, but uses something called as opportunistic wireless encryption, OWE, to encrypt all wireless traffic. Finally, IoT onboarding, it uses something called as device provisioning protocol, DPP, to quickly onboard IoT devices. I know that this module is quite big and it has a lot of information to take in, but I'm assuming that when you have come to this point, you must have studied at least something about wireless networks, their frequencies, channels, and other things, like even security features that are involved in your wireless networks, including the first earlier basics of electromagnetic spectrum, such things. Do have all of this in. Remember the most important points that I discussed, and I will meet you in the next module. Okay, so thank you very much for listening and watching this video. Thank you. Take care.